All right, guys, this is it. We are down to the last two convergence tests, the ratio test and the root tests. And I would say that this might be one of the most used, followed by one of the least used tests. We're going to see the ratio test get used a bunch in the second half of this chapter when we move on to Taylor series. But we'll learn them both because that's what we do here. So the ratio test is nice. It works whether the series is alternating or not. We do consider the absolute value of the ratio of consecutive terms, and if the ratio of the next term divided by the previous term, the n plus first term divided by the nth term, that order matters. If that ratio approaches any value that's less than 1 as n goes to infinity, then we say that the original series converges absolutely. If that limit is greater than 1 or is infinite, then we would say it diverges. And notice that there's no or equals to here. There's no or equals to here. Once again, we see that the number 1 is kind of an important boundary between convergence and divergence, just like in the P series, just like in the geometric series. But this time the 1 is inconclusive. So we don't like to see 1 because that means that the ratio test is not the test for us in this particular case. So we really like the ratio test for things that have a lot of common factors, namely factorials and exponentials. It really works out nicely for those. So let's take a look. The ratio test for convergence of infinite series. All right, so we take a look at this and we say, well, exponential grows pretty fast, but not as fast as factorial. So the nth term test, I think, is going to be inconclusive because the limit of the individual terms is going to head to 0. So let's not even worry about doing that. We'll just go ahead and jump into the ratio test, which says we'll take the limit as n approaches infinity of the absolute value of the ratio of consecutive terms. Again, the n plus first term should be on the top and the nth term should be on the bottom. All right, so we can do that, no problem. So we'll put a sub n plus 1 in the numerator. That's going to be 2 to the n plus 1 divided by n plus 1 factorial. And then we'll put a sub n in the denominator. That's going to be 2 to the n divided by n factorial. Okay, so we're dividing fraction by fraction. So that means that we can divide. Whoa, where'd it go? Oh no, come back. That means that we can divide, we can multiply by the reciprocal. Sometimes I really dislike OneNote. All right, here we go. So we're going to take this fraction, which is 2 to the n plus 1 divided by n plus 1 factorial. That's my numerator of my original fraction. I'm going to divide that by this fraction, which is the same thing as multiplying it by its reciprocal. So the n factorial goes on the top, the 2 to the n goes on the bottom, and then we have to reduce. Okay? So actually, instead of crossing things out, let's think about this and maybe explain why things divide out. All right, so in the numerator, why is this red now? Okay, fine. In the numerator, we have 2 to the n plus 1, which I'm going to write as 2 to the n times 2 to the 1, which should make some sense, right? Because that's just how many factors of 2 we have. And then I'm going to leave the n factorial alone. All right. The reason I'm going to leave the n factorial alone is because I noticed there's n plus 1 factorial down here. So I'm going to write n plus 1 factorial as n plus 1 times, you guessed it, n factorial. Remember, that's the recursive definition of the factorial function. And then we also have in the denominator this 2 to the n. All right, the reason I wrote it like that is because it makes it absolutely clear that we've got a common factor of 2 to the n on the top and the bottom. We've got a common factor of n factorial on the top and the bottom. And what we're left with is a much, much simpler looking fraction. The numerator is 2. The denominator is n plus 1. And as n goes to infinity, this fraction approaches 0. And the important thing about this value is that it is less than 1. Remember that 1 is that magic value between converging and diverging values. So because the ratio of consecutive terms tends towards 0, tends towards a value that is less than 1, we can conclude that the original series converges absolutely. Normally, we don't need to worry about stating the absolutely, but it is true. Converges absolutely by the ratio test. Don't say the RT, because then I might think you're talking about the root test. All right, so that is the ratio test. Let's try another one and see how that one goes. Another one that has exponential expressions. So we're thinking that this is going to work well with the ratio test, but it also has this polynomial, this n squared. So that's not going to be as pretty, and we'll see why. I still like the ratio test. We'll still give it a try. I think it'll still work. I'm not so worried about it. I like to start every ratio test by rewriting this, and I suggest you guys do the same, simply because repetition will drill it into your brain and you'll remember, oh yeah, that's the ratio test. And then I don't like to write the mega fraction over fraction, because then it gets really tedious to rewrite things over and over again. So I know that the n plus first term is going to be in the numerator, so that's not the one that I flip. So the n plus first term is going to be all of those terms, but replacing n's with n plus 1's. Right? So this n gets replaced with an n plus 1. This n gets replaced with an n plus 1. N plus 1 plus 1 is n plus 2. And this n gets replaced with an n plus 1. Now, I don't have any room to put a denominator here, because I'm not going to write a fraction in the denominator. Instead, I'm going to go ahead and multiply this by the reciprocal of the thing that we're dividing by. Multiplying by the reciprocal of a sub n just saves us a little bit of time. 3 to the n goes on the top, n squared goes on the bottom, and 2 to the n plus 1 goes on the bottom. All right, now if you want to rewrite to show all the different factors, you can. I did that on the last example simply for clarification purposes, but we're going to see this enough times that hopefully we can realize that we've got n factors of 3 on the top, we've got n factors of 3 on the bottom, and then an extra factor of 3. So we still have 3 raised to the 1 on the bottom. We've got n plus 1 factors of 2 in the bottom. And we've got just one more than that number of factors on the top, right? So we're subtracting exponents because we're dividing like bases. Now, the reason I mentioned that polynomials don't go so nicely with the ratio test is because n plus 1 squared doesn't share any factors with n squared, so we can't reduce that. But we still can deal with this because we know how to deal with limits with polynomials. So that's really not so bad. It's just we don't have as much that cancels out this time. So what's left? We've got 2 on the top, and we've got an n plus 1 squared on the top. We've got a 3 on the bottom, and we've got an n squared on the bottom. Okay? I'm not going to spend any time expanding this out because I know that this is a degree 2 polynomial. I know this is a degree 2 polynomial. I know the leading coefficients are 2 and 3, so I know that this limit equals 2/3. Oh, okay. So we're done, right? We just need to say, well, that's value is less than 1, therefore the series converges. Absolutely. Absolutely it does. By the ratio test. And that's pretty much how the ratio test always works. Unless we end up getting a limit that equals 1, then we have to say, oh, it doesn't work, and we have to find another test.